start this lecture. I will speak about calculus of Günther's derivatives, which are tangential derivatives, and about equations and all auxiliaries about on the surface, how it happens on the surface, to consider different differential equations, and we will end up with the derivation of some equations, for example, for shells. How to derive, with the help of these tools, equations for shells. Here is the content, but it might change a bit still, so don't pay much attention on it. But anyway, the first part will be about calculus of differential operators on hypersurfaces. Okay. Let me start very elementary definitions. What is a hypersurface? Of course, most of you knows it, but since it's this lecture, I consider it important to define everything precisely. What is a hypersurface? Hypersurface is a particular case of manifold when this set hypersurface is embedded in Euclidean space Rn and has dimension less than how to say, if the dimension of the Euclidean space n, the dimension, sorry, yes, oh, sorry. Of course. Here we are. If the dimension of space is n, then dimension of hypersurface is n-1. For example, the surface of this sphere, or ellipsoid, or in three-dimensional space, or in any n-dimensional space. And the exact definition is such that we have set in Rn, set, it's here is depicted as the surface, and this set is covered by subsets, small subsets. And these small subsets, each of them is mapped on domain in Rn-1, in n-1 dimensional domain. You know well that the sphere cannot be mapped on a compact set. The surface of the sphere you cannot map continuously on a compact domain on n-1 dimensional compact domain. You need at least two pieces to divide it in two pieces to map it and make it and this will be then the compact mapping on the compact sets. So any manifold and hypersurface also. And what we have, this surface is C0 is the image of some n-1 dimensional domain with the help of function theta yot. Okay. Also, theta maps omega yot to C yot. And thetas, this function theta, are called local immersions. And their derivatives, it's easy to trace that their derivatives are tangential vectors. Tangential vectors, they are tangent to the surface. And these vectors constitute covariant basis. Covariant basis vectors constitute covariant basis. And by B-orthogonal system, B-orthogonal means that the scalar product in Rn of these two vectors, G subindex yot and G upper index k, is delta GK. So it's orthogonal system of vectors. then this GK are called contravariant bases. Contravariant bases. Any tangent vector field U can be represented in three forms. One with covariant vectors, one with contravariant vectors, and one with, again, I forget, sorry, in three types: covariant vectors, contravariant vectors, and, well, the Formula One. And the canonical basis or natural basis in Rn. We have three representations, and notations for the coefficients is different. U with upper index G, U with lower index G, and U's G0. So we make difference between these representations with these formulas. And EG is, of course, as I told you, natural basis in R. This consists of zeros and one, they are basis in Rn. Okay. The gram, the gram matrix, it's very important matrix in differential geometry. Gram matrix is the consists of scalar products. It's well, it's compiled of scalar products of covariant vectors. Covariant vectors. It's gram matrix, and also yeah, and so yes. And here, it defines metric on this surface. With the help of the gram matrix, it defines the metric on this surface. What means metric? The scalar product is defined of two elements, x and y, taken from the points on the surface, are defined the metric with the help of this gram matrix. And well, it's yes, on the right side you see this scalar product in Rn. It's written also here how it's defined. Scalar product in Rn. So now we have the metric on the surface, and of course the distance. If we have the metric, we have the distance between two elements. X minus y is then square root from the from this scalar product of x minus y on itself. Moreover, the square root from the gram determinant defines the measure, from the determinant, yes, defines the measure of the surface. Now you see how important it is. So you can define with the help of it integration on the surface. Integration is defined with the scalar, with the square root from this gram matrix. And well, the inverse matrix to the gram matrix is compiled of scalar products of contravariant bases. Contravariant bases. And it's called the contravariant metric tensor. Contravariant metric tensor. Well, we don't need to construct special inverse. Special inverse is constructed with the help of the contravariant basis vectors. An alternative equivalent definition of hypersurface. There exists at least three definitions of hypersurfaces, but this definition, which is equivalent to the first definition, which we gave as a definition as a particular case of manifold, is very important. Why? I will explain it in a few seconds. If there exists a function such that it has gradient non-zero gradient in some set. Non-zero gradient is written here. Gradient or derivatives, vector of derivative is not zero. Well, it's compiled of the derivatives, partial derivatives of this function. And those points where this function becomes zero, it is announced as a hypersurface. Any hypersurface in the first definition can be represented with the help of this implicit function. It's called implicit function or implicit definition of the hypersurface, and vice versa. Any function, any hypersurface which is represented with the help of implicit function can be also defined with the help of first definition as a particular case of manifold.
Презентация в Zoom не двигается.
Pardon?
Презентация в Zoom не... все.
Oh, I
Okay,
again
okay.
forget to go further. No, it's okay, I think. It's okay. Yes. Definition 3 is a definition of a hypersurface. Now about nu. Yes, everything is correct. Here, nu is a normal unit normal vector field, outer unit normal vector field. At every point of the surface, we have vector nu, which is orthogonal to the surface, means orthogonal to all tangent vectors. And this vector field is very important for us. And it is very important also that if we have the implicit definition and we have implicit function phi, then this normal vector field can be defined as a normalized gradient. We take the gradient of this function, divide it by the norm of this gradient, and it is unit normal vector field, vector field now, and this is just the vector field which we need, the normal vector field. In what follows, this normal vector field will play a very important role, because all definitions of derivatives on surfaces and many things are defined with the help of this normal vector field. And it is also important that in differential geometry, many functions and many definitions are based on local definition. It's not global on the whole surface, but it's local definition. And with this normal vector field is a global vector field. It's defined everywhere with one formula. And with the help of it, we will define many things, including for the tangential derivatives and so on. And here is the picture. This vector field we can consider in the neighborhood of the surface, because the function, implicit function, is defined not only on the surface, but in the neighborhood of the surface. And if we normalize, we will get some vector field in the neighborhood. But it is not a correct extension of our vector field, normal vector field. I will speak about this a bit later. What is the correct extension, and that this one is not a good one for this. Here is the picture, some surface, and this normal vector field you see, nu. It's orthogonal to the surface. Okay, the components are new bold components are new one, new n. We will use it in next pages. If S is at least too smooth, I mean the function which defines the surface, I mean this mapping functions or this implicit function, if they are too smooth at least, then this vector field, normal vector field, no, tangent vector field, sorry, normal vector field, unit normal vector field has this property that the derivative dg nu k, dk nu g is equal. And this is called gradient vector field. In such case, such field is called gradient vector field. It is remarkable that the inverse assertion is also valid. It's proved by Massari and Miranda in their book that if we have some vector field which is gradient type, then exists surface where it is normal vector field. So it's, how to say, is reversible, this statement. And definition now. What is the normal extension? Proper extension of the unit normal vector field. Proper extension is such an extension that this property of to be normal vector field is maintained. So there exists some vector field in the neighborhood of the surface, n capital G, that this property dg n capital K is equal to n dk n capital G is maintained. So and this normal vector field has also this vector field has also norm 1. It's a unit normal vector field with this property to be normal. Then as I mentioned, as I told you in the previous page of slides, in previous slide, we have the naive extension of our normal vector field, which is gradient of implicit function divided by its norm. It is, of course, defined in the neighborhood. But it is a first exercise, if somebody wants to test himself, that this naive extension is not correct. It's not the proper extension. There exist examples when such an extension turns out to be not normal vector field. But this is a bad news, but a good news is the following lemma, which we prove together with my colleagues, Eugene Shargorodsky and George Tepnadze, that very, how to say, very direct and naive, also quite naive extension of our vector field. What an extension. We have normal vector, yes, and we slide our normal vector to the normal direction. So we get a normal vector field in the neighborhood. And this is the proper extension. This is proper extension. And maybe it seems strange, but this such extension is unique. There is no other proper extension of the normal vector field. Only this extension is normal. And well, how it was proved? It was quite easy since we had a very important theorem about aconal equations. Aconal equations were considered by many authors, but Maslov and Fedoryuk, Soviet mathematicians, proved such things that solution to this boundary value problem 7 is unique. What problem is this? We should find the function phi, which gradient is norm 1 on the surface, on the domain, then function is 0 on the surface, this function, and it coincides with the normal vector to the surface. So it's direct solution to our problem. That such problem, as they proved, has a unique solution. So it was quite trivial to adapt this to our purposes. Okay. Now we come to the topic tangent differential operators. If we are on this surface, we cannot take derivatives in any direction. It's clear. If function is defined only on the surface, you cannot take the increment of the argument at any direction. You can take increment of the argument only across the surface. So if we are on the surface and the coordinate derivatives there don't work. What works there is the tangent derivatives. And how it works. Imagine we have a surface and we have tangent vector field. At every point we have a tangent vectors. What we do, it is well known that then we choose point, arbitrary point, and there exist curves. There exist curves, which is called flow. And those curves have the property that these vectors from our vector field are tangent to it. Yes, that's flow. Now we can take increment of the function across this flow. It's correct. Then the difference we divide by the distance between 2 points and take limit as a usual definition of the derivative. And it will be the tangent derivative across this fixed vector field, which we had. But only tangent vector field. With other fields, we cannot find this flow and we cannot define the derivative. And it is represented here, this derivative, in correct form, in formula 8. Okay. Well, if the function is defined in the neighborhood of the surface, then you can relax and define the derivative with the help of coordinate derivatives in Euclidean space with the formula 9. You take the coordinate derivatives, multiply it by the components of the tangent vector. You take simply gradient of the vector field and multiply it by the vector field, and this will be the derivative across this vector field. It's equivalent to this definition, what was given in 7. But the 7 is correct definition if function is defined only on this surface. Okay. Further, we will concentrate on a very concrete tangential differential operators. We call it Günther's derivatives. Why Günther's? Günther was the mechanist in Soviet Union in 30s. He wrote book. He lived until 40s somewhere, but in 30s he wrote book in mechanics, and he used such derivatives, but very in restricted form. Then I have seen this this definition in the book of three-dimensional ellipticity written by Kupradze, Burchuladze, and so on, Kegelia and Bashalishvili. In mechanics, it was common to use these Günther's derivatives. But I realized that it is an important tangent differential operators, and I will try to make it clear and to convince you that it's really important and interesting tangential derivatives. When we come to definition of gradient, divergence, and Laplace-Beltrami operator on the surface, you will see how interesting formulas we will get for them. Okay, and how it is defined. Tangent vector fields across which the Günther's derivatives are defined is just projection of the coordinate derivatives from Rn. We have EG, you remember, consisting of zeros and one. Coordinate derivatives in Rn. I mean, coordinate basis, classical basis in Rn. If you take projection of it on the surface, of course you get the tangent vectors, and take derivatives across these tangent vectors. Then you get Günther's derivatives. Another, direct definition is such, you see here, dg is equal coordinate derivatives subtracted by nu g normal derivative. Normal derivative is derivative across the normal vector field. But this cannot work in such a form, dg minus nu g d nu, cannot work for functions which are defined only on the surface. Only on the surface, then you have to define it as with the flow, a flow across these vectors dg, which are projections of eg. And and these derivatives, dg's, as I told you, is a projection of eg's on the surface. What is the deficiency here with these derivatives? These derivatives, as you understand, we have in Rn, we have n basis vectors, EGs, n vectors. And when we take the Günther's derivatives on the surface, we get n Günther's derivatives. Of course, they cannot be linearly independent. They are linearly dependent, but they are all important. At some places where the direction of the normal vector and direction of normal coincide, one of these Günther's derivatives eliminates simply, becomes zero. But you cannot throw away one of them. Then you cannot write everything in correct form. You will see a bit later. Okay, this is some disadvantage, but not a big one. Okay. Another important example of tangent derivatives are Stokes derivatives. Why Stokes? Because it comes from Stokes' formula, which we will see. It's here. No, not here. Next slide, perhaps. Stokes derivatives, which are mgk nu g dk minus nu k dg. Why it is tangential derivatives? Because it is derivative across the vectors mgk, which is just written here. It is nu g ek minus nu k eg. If you have doubt that this mgk is a tangent vector, you just can take multiplied by nu. If you multiply by nu, the first summand, nu g ek, gives you nu k, nu g nu k. And the second subtracted by nu g nu k, 0. So multiplication by nu gives you 0. And this is the test for the vector to be tangent, yes? Multiplied by the normal vector field, it should be 0. Identically 0. And it happens here. MGK is very important also, but here also some disadvantage because this MGK, when G is equal to K, is of course 0. Also, MGK is equal minus MKG, but nevertheless, they are important. You will see the importance in some next formulas. Now, if we have the Lipschitz domain. Lipschitz domain means that the boundary of this domain is might have angular points and so on, and can be defined with the help of the Lipschitz function. This implicit definition of such surface will participate in, but there are many other definitions of Lipschitz domains. Okay, if we have the Lipschitz domain, then we have the important Gauss formula, which is which I think everybody of us had at the university. That if you take the derivative of function inside the domain and take integral on the domain, it is equal to the integral on the surface, but from function multiplied by the corresponding component of the normal vector. Formula 11. So this is well-known Gauss formula. From the Gauss formula can easily be derived the Stokes formula, which I mentioned. These operators MGK appear in Stokes formula. And to convince you that it is really easy, about Stokes formula. Stokes formula states that integral MGK f on the surface is equal always 0. This integral, of course, it's no wonder when G is equal to K, but in all cases, it is 0. Proof. I will give you only very short proofs, and other long proofs are in paper, which I can share with you. It's about more than 200 pages, not published, but there is everything proved, explicitly, no problem, if you are interested in some proofs, which I will not give here. And more detailed analysis and some more material you will find there, of course. You just write me email and I will forward you this manuscript. Okay. First of all, we take the function which is defined, also this formula up. Sorry. That's why when it is connected to each other. Yeah. Stokes formula here, formula 12. And now the proof. First of all, we can, from the beginning, take the function which is defined in the neighborhood of the surface. Neighborhood of the surface, and not only in the domain, but in some neighborhood, which we can extend the function. Always extend from the surface and from the domain. There are many methods. One of them, such methods, direct methods in function theory, is described in Stein's book, celebrated Stein's books. There are in many others also. But another definition, which is understandable for those who are engaged in the boundary value problems for differential equations. If you have function on this, you solve the Dirichlet problem. You have function on the surface, you solve problem, and Dirichlet problem means the Laplacian of this function is equal to 0, and on the surface, traces coincide with this given function, and you have the extension, and so on. We extend this function. Now, we take two derivatives of this function. Well, it is also smoother. For the Stokes formula, you don't you need only that the function is in Sobolev space W1. I mean, function and its derivative belongs to L1. I mean, integrable function. If it is so, the Stokes formula works. But in our case, we suppose that the function is smoother. For example, two derivatives exist. And belong to L1. Also, Sobolev space W2 belong to Sobolev space W2. Then we take two derivatives and apply the Gauss formula. You see here. Sorry, you don't see, but now you will see. Two derivatives, and you apply Gauss formula. And then now you replace the derivatives and again apply the Stokes formula, formula of Gauss. And now take derivative. Of course, the left hand side will disappear because since function is twice differentiable, these mixed derivatives disappear, and you will get Stokes formula. How to go now to W1? By approximation, a standard procedure, no problem. And why this formula is valid for the function which is defined only on the surface? Because these derivatives in formula, which we have, derivatives in the Stokes formula are tangent derivatives, so no problem that you can extend it also for functions which are defined only on the surface. Yes. So this Stokes formula is proved. From Stokes formula follows that Stokes derivative is skew symmetric. What means skew symmetric? It means that MGK phi integrated with another function psi is equal to minus phi multiplied MGK psi. So it jumps from one function to another and throws out minus. It's skew symmetric. It will be no minus and it will be symmetric. Skew symmetric. And why it is true? It is very, very easy to prove, of course, because of the Stokes formula. Because the Stokes formula, we know that Stokes derivative is linear derivative. It is combination of usual derivatives with some coefficients. MGK phi psi, well, Leibniz rule here works. MGK phi multiplied by psi is equal, formula is written here, MGK phi multiplied by psi is equal to MGK phi multiplied by psi and phi minus phi plus phi multiplied by MGK psi. And then you apply Stokes formula. And Stokes formula gives you what I have written in, because the left-hand side disappears due to Stokes formula, and the right-hand side gives you this rule of that the dual to Stokes derivative is the minus Stokes derivative, or it's skew symmetric. Okay. Due to equality, which is easy to check, that the Günther's derivative is just combination of normal vector field component with mgk. It's written here. dg is equal sum of the ng dk. dg is equal sum of nk and mkg. It's easy to prove because the first summand of mgk disappears and second disappears, and the first summand gives you dg. Because nk square, sum of nk square is equal 1. You remember that it's unit vector. After this, this formula gives you now interesting formula. What is the dual operator to Günther's derivative? The dual operator or adjoint operator to Günther's derivative is minus Günther's derivative and plus nu g, its component of nu with the same index, multiplied by something which is h0 and which is the mean curvature of the surface. It's interesting formula. Since we are not on the flat domain, which is on the surface, now comes into play the mean curvature of the surface. Mean curvature disappears, of course, when you are on the flat domain, because it's known that curvature describes the curvature of the surface, and of course it disappears when you are on the surface, when you are on the flat domain. Well, this is a result of this equation, equality, with the dg represented by the Stokes derivatives, and skew symmetry of the Stokes derivative. And well, then you need to commute nu g and dg, and nu g dg commuting nu g with dg gives you the mean curvature. Yes, well, mean curvature, of course, normalized mean curvature, because mean curvature should be divided also by, if the dimension of the surface is n, by n minus 1. Surface is n minus 1, you have to divide by n minus 1. But it's constant only. Partial integration formula with the help of Günther's derivatives. You know, on the partial integration on Rn has no how to say, while partial integration has no extra summands, just you can put dg from one function to another, just the minus will appear in front. And in the case of surface, it gives you also the curvature, as you see, nu gd. Well, but this is just the consequence of the formula that the dual to our Günther's derivative is this minus Günther's derivative plus nu g mean curvature. It follows from it. So now we know how to take conjugate differential or dual differential operators. If surface has boundary, then we have to consider the normal vector field to the boundary. But to the boundary, normal vector field is not unique, of course. But this normal vector field, which we consider, should be also tangent to the surface. So two conditions: tangent to the surface and then normal to the boundary. Then it's defined uniquely, not uniquely. You need also to be clear. You need outward unit normal vector or inward. We take normally outward unit normal vectors, which shows out of surface. Okay. if we have such a situation that we need to take the dual operator or conjugate operator on the surface with boundary, then you have to use this formula here. And what if the surface had no boundary, the last term disappears. But if it is surface, if the surface has boundary, then you have to take into account the last formula as in Gauss formula. It's how to say, it's the analog of Gauss formula for the surfaces. But now comes into play this normal vector field to the boundary. Yes, this additional last summand gives you a term which appears when the surface has boundary. So these formulas are proved. Gauss formula on the open surfaces have the form that dg phi is equal nu g phi and plus what, formula 16, that the normal derivative of function integral from the normal derivative, it's the, as in classical Gauss formula for domain, it's integral on the boundary, nu g phi. Oh, sorry, again. Yes. Sorry. Here are these formulas which I was telling you, that the Günther's derivatives, the partial integration with Günther's derivatives, when you replace the operator Günther's derivative from one function to another one, in Rn it gives no additional term, just minus. But in the case of surfaces, it gives also this, you see here, again, this mean curvature, additional term. And integration by parts. When you just replace one function from on the surface, replace the Günther's derivative from one function to another in the product. Oh, sorry. Yes. Then you have some additional term as in Gauss formula. It's just as the Gauss formula, but the normal derivative to the boundary appears, and normal vector field to the boundary, which I was speaking about, and also appears this curvature. And Gauss formula has on the surface has this form 16, that the normal derivative from the function is the, as in Gauss formula, first summand is this, as in classical Gauss formula in Rn, in domain, in Rn, but has additional term, which is on the surface, again, with the help, expressed with the help of involving the mean curvature. Consider tangent vector field. Then the operator, now we came to the definition of what is the gradient and divergence. For this, we take the differential one form, which is defined as the derivative of function with respect to this vector field. Yes, sorry. Thank you. Yes, here, omega is one form, and is a differential form, one form. The form is correctly defined because the differential operator is tangential and can be applied to a function which is defined only on the surface. Then for given f, there exists a vector field which is denoted by nabla SF, such that this differential form is represented as a scalar product of this vector field and F and V. Okay, and now this is a definition of gradient of function. Very implicit, I can say it's not clear definition. We know only the existence of it. But it is interesting. Yeah, the gradient, what maps it, it maps C1 functions, I mean, the functions which have continuous derivatives or derivatives in L1 Sobolev space, maps to a tangent vector field. And the surface divergence, Now, so we defined the surface gradient. Surface divergence is the dual operator to it. Dual operator. Dual operator is means what you have in the formula 17. Dual operator. So now we have the definition of surface gradient and surface divergence. And the first formula, which I promised you, interesting formula with the Günther's derivatives, that when you have Günther's derivatives, you don't need to think how to define the gradient and divergence. You just take, as in classical case, derivatives. When you are in Rn, you take derivatives, coordinate derivatives, and compile the gradient and divergence. In the case of surfaces, you take Günther's derivative and compile gradient and divergence in the same way. The vector consisting of Günther's derivatives gives you gradient, and the sum of these derivatives gives you divergence. And it is proved. I will not expose the proof here, but it is proved in this paper, which I told you. It is proved that this coincides with the definition which I gave you before this. That is first interesting results which attracted our attention, my attention first. And then I was in America with Marius Mitria and Dorina Mitria. We wrote a paper about those, about Günther's derivatives and how to apply it. And we calculated all this, and it's exposed everything there in this paper. Yes. And what is then the Laplace-Beltrami operator on the surface? Analog of Laplace operator on the on Rn. Laplace-Beltrami operator on the surface is just as in Rn, is just a composition of gradient and divergence. You take first gradient and then apply divergence. You get the Laplace operator, yes? And in the classical differential geometry, it is same. You take gradient and divergence. In this case, which we have here, with the help of, we defined it with the help of Günther's derivative. You have very nice formula that the Laplace operator on the surface is just square derivative, sum of square derivatives of function, as in classical Rn, in space Rn. The Laplace-Beltrami operator is represented in this form. And it is clear also from this definition, it's, I forget to mention that, I forget to mention that gradient and divergence, no, I mentioned it, but from the first definition, but defining gradient and divergence as the, with the help of Günther's derivatives, they maintain the properties that they are conjugate to each other with minus. So here you will get it easily that this operator is self-adjoint. Laplace-Beltrami operator on the surface is self-adjoint. And it can also be represented not as the squares of Günther's derivatives, but also as the squares of Stokes derivatives. But you should be careful because Stokes derivatives are symmetric. And if you take all derivatives, then you have to divide by 2. Okay, lemma. Time. Yeah. Slide. No, I think. Yes, sorry. Yes, you're right. Next slide. Yes, here is the Laplace-Beltrami operator in Formula 20. It's the sum of squares of Laplace of divergence and gradients. I have last 5 minutes, yes? Yeah. Okay, and lemma that if the what I missed here to write that this gradient applied to phi is the surface gradient. So it's now with nabla with subindex s. Nabla subindex s phi is equal 0. From it follows that function is constant. The classical result in Rn, yes, you know, if all derivatives are 0, the function is constant. It is same on the surface. It is same on the surface. And it is proved actually easily because if you have function on the surface, you can extend it in the direction of normal as constants. You will get function and then the Günther's derivatives will coincide with the coordinate derivatives. And then you can derive this property quite easily. But it's important to know that if all Günther's derivatives are 0, the function is 0. Well, Laplace-Beltrami operator has, well, Laplace-Beltrami equation, delta S phi is equal to 0, has only a finite number of linearly independent solutions. We will speak later about these solutions, but here is the very easy proof that it is so because Laplace-Beltrami operator is compiled of gradient and divergence. And then when you take Laplace-Beltrami operator over psi multiplied by psi, you throw one of these gradients throw to another function, and then you will get that the gradient is 0. And if the gradient is 0, we know that the function is constant. Some most basic properties, of Günther's and tangent derivatives. But to explain all of them, it needs time because here are, I think, about 9 such properties. So better I stop here. Thank you for the attention.
Since you have the only microphone, if there is a question, please repeat the question. We have no microphones. You are the only one with a microphone. So if there is a question, please repeat the question.
I have problem also to hear from this one.
Okay, questions, please. So let me then
maybe in private.
let me then ask. First, if you speak about the outer normal, you speak about surfaces without boundary, right?
No, with boundary also. We have outer normal.
Because then
we choose them.
Okay, but then it's not outer, it's just your choice.
Yes.
Yes.
We just have to fix what is outer and what is inner.
And the second question, you haven't said it explicitly, but do I understand properly that you consider finite surfaces finite surfaces.
Yes, mostly yes.
Because the lemma by your and Shargorodsky and Teknadze would not be valid for infinite surfaces.
Yes.
Yeah, you're right.
No, with infinite surfaces, it needs some additional conditions. Of
Yeah,
course.
yeah.
We don't touch it. So,
Okay. Anyhow, other questions?
okay. In private conversations, we can clear. these
Okay.
questions.
I see no questions, so let's say, well, again. Or talking break. This is fine, but I mean, it does not go to Zoom. Yeah. That was important. Yeah. I'm smoking up voice. Probably. Not smoking up, you don't do it out. That's fine. Okay, welcome back after the coffee break. Boss. So the next speaker is Berger Torebek, local speaker, and his title is again quite long, so
Okay.
really so.
Yeah.
Go ahead.
Thank you. Thank you for the introduction. Good afternoon, everyone, dear participants, dear guests, dear students. First of all, thanks for the organizers to giving me this opportunity, to inviting me. It's great honor to me to be here and give a talk for young researchers, for mathematicians with a different country. And within these 4 days, I will discuss with you about semilinear parabolic problems, mainly about Fujita type critical exponents, and we will discuss about history and new results and about some open questions. Yeah, let me share first plan of my lecture. Today we will discuss about critical exponents for the heat equation given on the whole Euclidean space, and some of their extensions. And the second one will be about the critical exponents for the heat equations with non-localities and or with forcing terms. And the third lecture will be about critical exponents of the exterior parabolic problem. It means that for parabolic equation given on the exterior domain with different boundary conditions. And the last lecture will be about critical exponents for the heat equation in the bounded domain. And here a lot of students, and let us start with very elementary things. Let us repeat some elements from the partial differential equations theory. Let us consider this heat equation. This is first order evolutionary equation. And here U is the temperature distribution. And This is a Laplace operator. It means that this is a second order differentiation by space variable. It's a very famous equation, and it can be arise in a lot of physical process, including diffusion process, some reaction. As we will speak about the parabolic equation and the heat equation, and let us start with a linear case. This is two-dimensional case. If we consider two-dimensional heat equation, it can be present. This is sorry, and this very simple representation, and this is a three-dimensional case. And if you consider heat equations, this is first order differential equations by time, and we should put initial condition Cauchy data at the initial time t equal to 0. And also, if you consider on the bounded domain or some exterior domain, you should put boundary conditions. For example, this is Dirichlet boundary conditions, Neumann boundary conditions here, and is a derivative, normal derivative in the boundary. And also, we have this is mixed boundary conditions, or it calls sometimes Robin boundary conditions. And from the theory of partial differential equations, we know that the heat equation has a fundamental solution, and sometimes it calls a heat kernel. It can be represented by this formula. And the heat kernel has the following some properties. And first, it satisfies the heat equation. And also, if t equal to 0, it can be represented by Dirac delta distribution function. And also, it has a symmetry property like this. Also, it has scaling property like this. And also, the integral of heat kernel equal to 1. Because this is a normalizing constant here. As this is a normalizing constant, and integral of this heat kernel will be equal to 1. And if you consider the heat equation with some general initial condition, then the solution of the heat equation can be represented by heat kernel, by convolution of heat kernel with the initial function. And sometimes we can write it in this form or in this form. Okay, now let us discuss about what is the blow-up solution in terms of differential equations. First, let us consider this kind of first-order nonlinear differential equation with Cauchy initial data. Then it's not difficult to show that the solution of this problem can be represented by this expression. Here, A, some constant, A is the initial data, sorry. And if A is a negative, strictly negative, then we say that this solution exists globally. Globally here, I mean, it exists for any time. And if A is positive, then there is some local solution up to the time capital T. Here, capital T is 1 divided by A. A is the initial function. And if T goes to capital T, then our solution goes to the infinity. This phenomenon it's called blow up infinite time. Let us show another example. Let us consider the Korteweg-de Vries equation on the finite interval with this kind of boundary conditions and this kind of initial conditions. Then also one can show that this problem has this kind of solution. Here T star some constant between 0 and the capital T. And also here, there is a local solution up to the time t star. And if t goes to t star, then the solution goes to the infinity. Zero rise, also blow up phenomenon. Okay, now let us show some results for the semilinear heat equation. Let us consider this kind of semilinear heat equation given by the formula 1. Here, f of u is the local Lipschitz function. And we consider on the whole Euclidean space with initial data u0. And then it is known the following results about local existence. There exists some small time capital T such that the problem 5 with this kind of initial data has unique classical local solution on the time interval 0 and capital T. And also using the extension theory, it is known that the solution U can be extended up to the maximal interval 0 in the T max. Here, T max can be equal to infinity. In this case, we say that the solution exists globally by time. Or if capital T max is some bounded number, then in this case, there exists only local solution. And if T goes to this maximal time, then the norm of U of Tx goes to infinity. Okay, and there arises some natural question. When we can choose the time up to the infinity and when there will be blow up. First time this kind of problem considered Japanese mathematician Hiroshi Fujita in 1966. Fujita was a PhD student of Toshio Kato. And he considered this kind of model problem, a semilinear heat equation with power law nonlinearity. And initial data assumed that it is not non-negative. And he proved the following results. If P, this is a power of the U, if P greater than this number, 1 plus 2 divided by n, then for sufficiently small initial data, the problem 2 admits a positive global solution. And if P between 1 and 1 plus 2 divided by n, then the problem 2, the semilinear heat equation, admits no global positive, global in time positive solution. It means that there arises a blow-up phenomenon. T cannot be continued up to the infinity. And the critical case was left open in the Fujita's paper. Later, Hayakawa considers the two-dimensional case, 1 and 2-dimensional case, and Kobayashi, Shirawa, Tanaka consider multi-dimensional case, and they show that in this case also belongs to the first one. It means that there is also no non-negative global in time solution. There will be blow up. And the number 1 plus 2 divided by n is said to be critical exponent in the sense of Fujita. And okay, sorry. Let us try to prove these results using more elementary approach. For this, first we need to give some proposition about comparison principle. Comparison principle is some generalization of maximum principle for the heat equation. Let omega be an arbitrary domain of Rn. It can be bounded or unbounded, and let capital T is a positive number. And suppose that U and V from this space, and they has compact support, and assume that initial data of U less than initial data of V. And let us consider this kind of differential inequality. Here, f of U is a local Lipschitz function. Then U will be less than V. For example, this statement can be found in the book by Pavel Kutner and Philippe Souple, published in 2019. And to prove the global existence of solution, we will use this method. For this, let us consider this kind of function, z of xt. Here, epsilon is some positive number, here and 1 plus t power m. And m is also positive number, and k has this form. This is shifted heat kernel. And it's easy to show that this k satisfies the heat equation. Then we can calculate, we can put that to the semi-linear heat equation. Then using the elementary calculus, we can arrive this kind of results. We can take derivatives by time one times, and we know that the k satisfies the heat equation. Then if we take derivative by time and the Laplace operator to k, then it will be equal to 0. And finally, we have this expression, and we can from here we can get this kind of expression. And finally, we have this one. And from here, if we choose m as n divided by 2 minus k, here k from this range, then as p greater than this number, 1 plus 2 divided by n, then the set, then this interval is not empty. Yeah. Then using this fact, we can show that this term will be negative. Then from here it follows that this expression less than 1. It means that we can estimate this term by 1. And therefore, using these facts, we can arrive that this semi-linear heat equation by z will be estimated by this expression. And if we choose epsilon small enough so that epsilon smaller than this number, then we have that this equation is non-negative. It means that Z will be the super solution of Fujita's problem. If we choose, if we assume that initial function bounded from below by a Gaussian function, then the solution of semi-linear heat equation will be estimated from above, by this expression. It means that this function bounded for all time. It means that in this case, the solution exists globally. And let us prove another case. Suppose that P less than PF, critical exponent. And let us consider this function, capital U. Here, J of xt can be presented by this expression. And it satisfies this adjoint heat equation. And at capital T, it can be written by this delta distribution function, and also the integral of G equal to 1. And suppose that U0 initial function is non-negative, then capital U0 will be also strictly positive. And let us calculate the first derivative of capital U of T. Then we have, first we have this one, and instead of ut, we can put Laplace u plus u power p from the equation. And instead of gt, we can put Laplace g, also from the property of g. Then using integration by part formula, we can arrive to this expression. From here, we have that it will be equal to this term. And using the Holder equation, Holder inequality, we can arrive at this kind of expression, because here g integral of g equal to 1, and we have only this one. And finally, we can estimate u power p g, integral of u power p g, by this expression. Then we have, for capital U, we have this kind of differential inequality. And integrating this last inequality over the time from 0 to t, we have this kind of inequality for all 0 and capital T. And instead of time, we can put capital T, and then we have this formula 3. Also, we assume that U0 bounded from below by some constant A, strictly positive constant A, inside of some ball with radius alpha. Then for the U0, capital U0, we have this estimate from below. And finally, capital U0 can be estimated from below C capital T power of minus n divided by 2. And combining the inequality 4 and 3, we have this kind of inequality. And it means that we have this inequality. If P greater than critical exponent of Fujita, then the power will be the negative. And if we choose capital T large enough, then there will be contradiction. It means that T cannot be arbitrarily large time. It means that there arise a blow-up phenomenon also. The critical case, also I should mention before, the critical case was proved by Hayakawa for two-dimensional case, and for multi-dimensional case, it will be proved by these guys. But the proof was very complicated, and the more simple proof of these results was given by Fred Weisler in 1981. But we will skip the proof by Weisler. And now we will speak about some improvements of Fujita's results. In 1980, Soviet mathematicians Galaktionov, Kurdyumov, Mikhailov, and Samarsky, they considered porous medium equation with power law nonlinearity in the right-hand side. And they try to extend the Fujita's results to this equation. And they have, if P between M and the M plus 2 divided by N, then there is no global in time solution of this problem. And if P greater than this number, M plus 2 divided by N, then the problem porous medium equations has a global in time solution for some sufficiently small initial data. And they also skip the critical case. Critical case was proved later by Mochizuki and Suzuki in 1997. They also show that the critical case also belongs to the blow-up case. And Escobedo and Herrero considered system case. They consider two systems of semilinear heat equation. And they also show that if n divided by n less than maximum value of these numbers, then there is no positive in time global solution. And if n greater than this number, then there is a global solution for sufficiently small initial data. The results was published in 1991 in the Journal of Differential Equations. And also Ki-chan, he extend Fujita's results to the Riemann manifold first in 1999. And also he extends Fujita's results on the Heisenberg group. This result was published in 1998. And later, Pokhajaev and Veron extend these results of Jank for more general parabolic differential inequalities. And they obtain only non-existence results. And their paper was published in 2000 in the Journal of Manuscripta Mathematica. There is some mathematicians who made enormous contributions to the development of this theory. This is Howard Levine, American mathematicians, also Stanislav Pokhajaev, Russian mathematicians, Enzo Metidiori, Italian mathematicians, also here Caterina Bandel, Switzerland mathematicians, and Philippe Souple, French mathematician, and Ki-chan. He's also from USA. And there is also some books devoted to this directions. There is a book by Samarsky, Galaktionov, Kurdyumov, Mikhailov, published in 1987 in Russian, and later it was translated to English in 1995. And also there is a book by Metidiori and Pokhajaev in 2001. It's also in Russian. And also there is a book by Terence Tao about dispersive nonlinear equations, including Korteweg-de Vries type equations. And there is also a book by Pavel Kuitner and Philippe Souple, there is also a book by Caffarelli, Coles, Guo, Carlos Koenig, and Alex Vazur. Also a book by Russian mathematicians, Korpus, Vavtinev, Sveshnikov, Yushkov, and the second edition book by Pavel Kuitner and Philippe Souple, published in 2019. Okay, now let us consider the same problem, but with this kind of nonlinearity. Here we don't assume the positivity of solution. First time this kind of problem was considered by Ki-chan in 2002. And he also tried to prove the same results for the problem 5. And he proves that if P satisfies this condition. Here, PF is a Fujita critical exponent. And if integral of initial function is strictly positive, then the solution is not globally. There will be a blow up. And if P greater than Fujita number, then there exists sufficiently small initial data such that the solution can be globally in time. And he also gives some conjecture that it will be interesting consider the case when integral of initial function equal to 0, but u0 is not equal to 0. And the answer to this question was given by Rospinski in 2005. He considers the same problem. And he proves that if integral of u0 equal to 0, and if P satisfies this inequality, then there is no global in time solution of the semilinear heat equation. And if integral of u0 is strictly negative, then for any P, there is a global solution. There exists some initial data such that the solution can be exist globally. And okay, let us try to prove this statement. First result by Rospinski, and also first results by Ki-Zhan. For this, we use the test function method. It's a very famous method. First time, I don't know who used the first time, but for Fujita type critical exponent, it was first time used by Didas and Spruck in 1981. And later it was developed by Italian mathematicians on the Heisenberg group for elliptic equation. And also for the parabolic equation, it was developed by Pokhozaev, Mitidiori, and Ki-Zhan. And we assume that there is a global in time classical solution, and such that U belongs to the LP space. And let us consider this kind of function from this space. And we suppose that phi x t equal to 0 if t greater than capital T. And we can multiply this function. We can multiply equation 5 by this function, and integrating by parts, we have this expression 6. And here, all derivatives on the function phi, and also here, derivative by time. Also, we can integrate by part for t function phi. And using the Young inequality, we have this inequality. Now we are trying to estimate the right-hand side of the identity 6. And the second term, we can estimate by this inequality using the Young inequality. Okay, here maybe I will write more detail on the blackboard maybe. Board one. Here, we can write this one, write this one. Here, 5 power of 1 divided by p minus 1 divided by p. Here. Function p. And we can use the Young inequality here, and then we have this one. First term will be u power p pi, and second one, this one. And similarly, we can estimate the first term also. Then we have the similar inequality, but here we will do Laplace phi of the power p divided by p minus 1. And here C1 and C2 some constants. Epsilon is also a parameter of the Young inequality. And here we can choose the epsilon 1 and epsilon 2 by 1 divided by 4. And then we can obtain this kind of inequality instead of integral identity 6. Here, right-hand side depends only on the test function. And now we should estimate this term and this term. For this, we consider this kind of special form of test function. Function phi we will represent by this expression. Here, capital T and the capital R is a sufficiently large numbers, and the K and the L is also some numbers greater than 1. We suppose that capital psi from C1 and the capital phi from the C2 0 is compact support. And also we suppose that function phi and psi has this kind of properties. Then we can estimate the right-hand side. We can estimate this one and this one. Then changing the variables t by capital T tau and x by capital R y, we can obtain this kind of inequality for first term and this kind of inequality for the second term. Here BR is a ball with radius R. And now we can put instead of T R square, because and the T and R is large numbers. Then we can write this sum. We can estimate by this capital C R power of n plus 2 minus 2p divided by p minus 1. And finally, for the solution of our problem, we have the expression 7. And here, if we suppose that p less than 1 plus 2 divided by n, and we have that this number is strictly negative. And from here, we can passing to the limit. We can if R goes to infinity, then the right-hand side of the inequality 7 will be equal to 0. And this is a contradiction with the fact that the integral of u0 is non-negative, because we suppose that we assume that there exists global in-time solution, then this term will be positive. This one positive, this one is non-negative, and the sum cannot be a negative number. And the critical case, let us try to prove the critical case. Suppose that p equal to 1 plus 2 divided by n. And then we can rewrite the identity 6 in this form. And we can estimate here integral g1r and the g2r using the Hölder inequality to the right-hand side of this integral identity. we have these estimates, first one and second one. And using the previous calculations, for critical case, we have that G1R and the G2R is bounded from this function. And here we can pass into the limit when R goes to infinity. Then we can rewrite the integral G1R by these terms. Then if R goes to infinity, this will be from 0 to infinity. This one will coincide with the whole Euclidean space. Then finally, the limit of this function will be equal to 0. And similarly, the second one, GR2, is also goes to 0 if R goes to infinity. Then we can go to a limit in the expression 8. Then we show that the limit of G1 and G2 goes to 0. Then we have the similar one. This one plus this one will be non-positive. This is also contradiction, and it means that there is no global in time solution. And okay, now let us discuss the case when P greater than Fujita number. And from Fujita's results, we know that there exists global in time solution only for sufficiently small initial data. And but if U0 is large enough, then there is no global in time solution for any P. For example, it's easy to show using this approach. One can consider this kind of function. Here, k of x can be represented by this expression. Here, Cn is a normalizing constant. And it's not difficult to show that Laplace k of x greater than minus k. And then using the elementary calculations, we can show that the capital U satisfies this integral differential inequality. And this differential inequality, the solution of differential inequality can be blown up in finite time. So it means for large initial data, there is no global in time solution for any P. For this reason, Lee and Ni consider the same problem of Fujita in the case when P greater than this one. Because if P less than this one, we know that for any U0, there is no global in time solution. And they assume that the initial function can be represented by this polynomial. A is a positive number. And they show that if A less than 2 divided by P minus 2, then there is no global in time solution. And if A greater than this number, then there exists a global in time solution. This phenomenon is called the second critical exponent, or in sometimes Lee-Ni exponent. And okay, let me finish my today's lecture by some known results by Galaktionov and Pakhojaev. Galaktionov and Pakhojaev consider high-order case of Fujita's results. They consider, instead of Laplace operator, they consider m power of Laplace operator. And in this case, they show that the critical exponent of this problem will be 1 plus 2m divided by n. It means that from 1 up to this number, there is no global in time solution. And if P greater than this number, there is global in time. There exists global in time solution for sufficiently small initial data. and their results was published in 2002 in Indiana University Mathematical Journal. And later, Italian mathematicians considered the same problem, but for this kind of initial data. And they prove that there is some second critical exponent in the sense of Lie and Ni for the high order parabolic equation. And also Gazzola and Grunow considered biharmonic heat equation, but with this kind of more general nonlinearity. Here, nonlinearity can change the sign. And they also show that there is a global in-time solution if beta equal to 4 divided by p minus 1. And also the results was published in 2007. Yeah, it was my last page of presentation. Thank you very much for your attention.
Any explanation that this Fujita critical index depends on the dimension n, but your other critical index that you mentioned here at the end is independent of the dimension n.
You mean the second critical exponent?
Yeah, that was not dependent on n.
Yes, second critical exponent depends on the initial data.
Okay.
Yeah. For any dimension.
A little bit not so close connected. You have these cases where the initial value was indefinite, right?
Sorry, can you?
Where this function u0 was not of one sign. Could check the sign.
Yeah.
Can you also put something into the equation which changes sign, like something like signum? Like signum in front of the Laplacian.
Uh-huh.
I mean, it's not so clear what signum means. You have to define signum somehow.
No, if
Changes in the derivative. Sign changes in the derivative.
yeah, okay, but I don't know about global existence, but the blow up results will be the same. Blow up results will be the same.
Huh?
Yeah.
A single question, could we go back to the first galaxy or not?
Yeah, sure. You mean the quadrilinear case? Porous medium, yeah?
Laplacian,
Yeah.
yes, so the M would describe the porosity of the material.
Yeah.
So as a physical model, it M equal 1 is no pores.
Yeah.
Yeah.
This is heat
So
equation.
as a physical model, it makes sense between 0 and 1. Yeah.
For between 0 and 1, it will be slow diffusion equation.
Yeah, but
there is also the similar results, but I didn't show here.
It's
Yeah.
between all pores,
Yeah,
the
yeah,
material
yeah.
is non-existent and a full material.
Yeah.
Yeah, that's the range. And if M goes beyond this region, that's just a mathematics.
Yeah.
And another question, so all that critical exponents, they depend on the fact that your nonlinearity is of power type.
Yeah.
So are there criteria for other nonlinearities? The criteria for existence or non-existence of global solutions?
Yeah, there is also some results if f of u asymptotically can be represented by power law functions, then there will be also the similar results. Yeah, but in another case, I don't know.
Or your last chance. Yes.
Blood for hyperbolic equations is because of intersection of characteristics. There is some evident geometrical reason for
No, here I consider only parabolic case. And in hyperbolic case, the nature of hyperbolic equation is differently. I don't know. In this case, there is a lot of critical exponents. Critical exponents in the sense of Strauss, in the sense of Kato, something like this. And if you consider with damping term, then there will be the same result with the Fujita. There will be the critical exponent by Fujita, if you consider with the damping term. Yeah.
Now, so let's say.
Thank you. Thank you.
What is for today?
It's 6:30, or when-